Welcome back to Wheeled Mobile Robot course. So today what we are going to see more, you can say, combination of what you have seen in the last two lectures. So the previous lectures to previous what we have seen like what is kinematic control of a mobile robot, and the previous lecture we have seen actually like how to do a dynamic control with you can say second order aerodynamics. So the first order aerodynamics we have seen as a kinematic control, the second order aerodynamics we consider as a you can say dynamic control. So like that kinematic and dynamic we combined and give as a called cascaded loop. So that is what we call actually like a double loop or cascaded control for a mobile robot. That is what we are going to see in this particular lecture. So before going to see that this particular cascaded has another name called backstepping. So why it is called backstepping, that is also like we are going to see in detail in this particular lecture. So let us actually like move to the slide where we were actually like seeing about so what is backstepping control design and how that is going to see. So before going to see that, let me brief introduce so what we are going to see. So for example, you assume that this is the robot, okay. The robot would be giving two things. So the robot would give actually like I assume that the velocity of this and position of this. So I am taking this position as the outer loop, okay. So I assume that the eta desired is known and I am trying to control that. So this I am actually like trying to take as the primemost, okay. So then what I am trying to see that the eta desired dot also available to me. So this also like I am actually like combining it. So then what I can do it, so I am trying to do actually like a two-stage control. So where each stage I am controlling as a single you can say state control. So in the sense what I am trying to do it, so I will be writing this second order differential equation of the mobile robot, I will be writing in a two first order you can say state equation. So what then I will do, so first I will try to control this as 0 when t tends to infinity. Then I will see that this would be achievable only with the second state we call eta desired dot. Then the second case what I will take, this eta desired tilde goes to 0, where here I will not put this eta desired you can say dot as it is like coming from this derivative, okay. So that is the change which we are trying to incorporate. In the sense you can see like this is going to do one inner loop based on what you obtain that you call as eta desired dot, but this eta desired dot combined with another one we are actually trying to do. So this I will call as a control, okay. So then what you can see, this is outer and this is inner, that is what we are trying to do in this particular lecture. We will go in detail along with the lecture. So first for understanding this, you know nth order system can be rewritten as n first order system, right. So now if we write, that is what you call state space equation, but generally what we usually write, so x dot we will write as function of you can say x comma u comma t. I am just skipping that. So now this is actually like vector, but similarly you rewrite this nth order system into n first order system, then most of the people will write like this, okay. So x2 dot would be like function of x1, x2 and x3 like that, but this will not give any backstepping control design. So then what supposed to be for backstepping control design, the system supposed to be input affine. So you know affine, right. So it's supposed to be input affine. So in the sense every single state equation you write as a subsystem, that subsystem has supposed to be having a independent control input. You can see, right. So this x dot is actually like function of x1, but that is independent with x2. So now the x2 is actually like considered as a input for the overall x1 dot equation. So similarly x2 dot you can see that x3 is the independent input. So like that you go at the end where xn plus 1 I am calling as a u, this is what the original input, okay. This original input I am actually like rewriting. Now you see in that sense the nth order system I have rewritten as n you can say first order differential equation along with in such a way that it is input affine. Some people call it is a strictly feedback form, but you can take it either way, but it is an input affine system. So now then you can actually like recall what we have derived two subsystems in the robotics. One is what you call kinematic model, the other one is dynamic model, right. So now you can rewrite this into like this, you can say second order differential equation in the form of eta, or what you can write eta dot and zeta dot. Now what you can do, you can see that the second order differential equation I can write as a two, you can say first order differential equations, right. So that is what we are rewriting, you can see, right. So this is what I wanted. The robotic system I know like it is a second order differential equation, I am rewriting in the form of x1 dot and x2 dot, where x2 is actually like the second system, you can see state variable, where u is the overall system input. So that is what we are trying to make it. So for that we will recall this is what the equation we obtain in the kinematic and dynamic equation or derivation. So now we recall this into what we have seen in this way. So then what I can write, x1 I can write as eta and x2 I can write as a zeta, right. So then I can rewrite the remaining everything. So that is what I am writing in this form. So now I can see that I am recalling this equation, recall x1 as eta and x2 as zeta. So now I can actually like go ahead with what is f1 x1, in this case there is no function of eta, so then it is 0, right. And what is, you can look at is g1 of x1, so this is actually like x1, right, eta is x1, so this is look like g1 of x1. So in the sense what you can write g1 of x1 as what you call j of eta. So similarly you come to the second equation. So the second equation I am rewriting as like this. So then you can rewrite as tau. So you can see like this is g2 of x2, x1 comma x2, and this would be, you can say, rewrite as, so function of f2 x1 comma x2, right. So that is what I am actually like rewriting, you can see that way, right. So then f2 x1 comma x2 is actually like this equation, right. So whereas actually like this whole product would be your g x2, right, g2 x1 comma x2. So now these all obtained. So what you can see, so already you know this particular equation in the input affine form. So now you are actually like ready to use this particular model for the backstepping control design, okay. So now you know the u is nothing but tau. So what is backstepping, that we will see in the flow, okay. So now you know like this is what we have derived. So before that I will actually like recall what we have done in the motion control. So this we have actually like assumed that these are actually like given and these are available, and this is what we are finding with the assumption that the t tends to infinity, where eta tilde and eta tilde dot goes to 0, which is nothing but asymptotically or exponentially stable. So for that what we are actually like trying to write, so now there are two errors will come, one is E1, the other one is E2, where E1 would be the first system equation, where x1 dot I am writing as, so f1 x1 plus you can write g1 x1 into x2. If I choose x2 properly, where x1 tends to, you call 0, right. So now here I am actually like rewriting that in the other way around. If I choose this x2, I can make this E1 tends to 0 when t tends to infinity. So this is the general, but I am bringing with a closed loop. So what then supposed to be, I have to choose x2 in such a way that this equation actually like make it. So I am rewriting that equation. So where x1 dot as f1 x1 plus g1 x1 into x2, where I am differentiating this E1 dot. So why? I can actually like I can recall the Lyapunov stability. I can actually take the Lyapunov function as like this, okay. So this would be always positive, when it would be 0, when E equal to 0. If I take the derivative of this, then the derivative is actually like negative and negative definite. So then what I can say, that would be what you call a stable system. So now for that I am taking the differentiation this. So then what I will get, so this. So for that I am actually like trying to find out what is E1 dot. So E1 dot is actually like x1 desired dot minus x1 dot. Already I know x1 dot is in this form, right? I substitute that. So what you can see, this x2 is the control input that will come into a picture. So now what would be the x2? x2 would be the choice where the g1 x1 inverse, okay, multiply with all the other things. What all other things? So you can see that x1 desired dot, okay, so then plus f1 x1. So these all actually like going to come, right? So that is what we are also like trying to see. So for that I am actually like taking this e1 dot and I am actually like substituting this equation, since it is actually like f1 of x1 is 0 in this case. So straight away it is coming. So now I am actually like taking x2 as the input and I am actually substituting as a subsystem. Then what I will get? So this x1 tends to 0, right? So in the sense e1 tends to 0 in our case. So that is what we are actually like achieving it. So for that I am choosing this x2 in this form, okay. So now for that what I am trying to bring? So I am trying to bring the error dynamics as this way, okay. In order to find this error dynamics, what I know this equation, right? So here I choose x1 dot in such a way that, so this goes and it will give only k1 e1 as the residue, that to negative sign, then I am done. But what is x1 dot is in this form. So now this zeta I can choose in such a way that this is actually like happening. So that is what we have done here, where the simple first order error dynamics is actually like become 0. So then you can see that as long this k1 is positive, so this particular case is done. So that is what we have actually like taken care here. But what the condition here is, this x2 is not a control input, that you should be known. So then what x2? x2 is the state vector, right? Then what you have to do it, the x2 you cannot actually like play anything, right? But instead of that, what you can do a play, you can take x2 decide as a virtual control input for that particular subsystem and then you can do it. Then you can see that the x2 decide and x2 there would be a difference, right? This difference, if it is 0, then you are actually like achieved x2 decide as x2 or x2 is x2 decide, both are same. Then what you have seen in the previous, this is achieved, right? So in the sense what you are doing is actually like you are coming backward, right? So that's why it is called backstepping. In the sense the x2 you assume as a virtual input and you have done all the control strategy and then you are going the next system, and once you are going the next system, then you are actually like seeing that no, this is a state variable, I have to actually like go back and change it. So that's what you are actually like going in the backward direction. That's why it is called backstepping design. The design is based on, you can say, your previous state and then design and then going further. Since it is actually like only second order system, you have done only 2 step input, right? 2 stages where E1 and E2 you are calculating. Whereas if it is actually like nth order, then you would be doing every stage n times, right? You are going in a backward direction. So that is what we are actually like saying a backstepping. Now this E2 supposed to be 0. Then what you can see, the E2 can be 0 when this x2 dot, if you take the E2 dot plus k2 E2 is 0, right? In the sense what you can see, this x2 desired dot minus x2 dot, you can say supposed to be equal to something like k2 E2. That's what you have to write, right? So that to like minus. So then what you have to see, you have to choose x2 in such a way that this would be fulfilling. What is x2? x2 is actually like, you know, this is zeta dot, right? Where d inverse into tau minus n of zeta, right? So now you can actually like substitute the tau in such a way that this would be fulfilling. So that is what the second loop all about. But what one supposed to know, you have taken x2 as the input, but the x2 is actually like difference of, you can say, x2 decide minus error. This error need to go 0. For that we are actually like playing the further thing where the error dynamics E2 dot plus something into this form we are trying to find out. So for that what we are trying to do, we are actually like going back with your known. So this is actually like already known from the previous, you call what you call previous slide. So this you know, this is now become x2 desired. So that is what we are actually like used. So now based on that you are going further. So what further? You are taking x2 dot equation and you know this u equation. So now you can actually like choose in such a way that this particular case coming into a picture, you substitute that x2 dot and then you replace and then find the tau. So the tau will come in this form. Okay. So nothing but that is u. So now you rewrite that into a generalized way where this E2 is actually like you know x2 desired minus x2, where the x2 desired you can write in the other form, then x2 desired dot is actually like in this form. So here you can see that this is nothing but eta double desired and this is actually like eta dot desired, and you can actually like see that here it is eta desired minus eta, right. So whatever you have given, that all actually like resolved and got it as a simple input, that is what we are actually like used. So in that sense what you can actually like see that, so you can actually like ensure the closed loop stability, but we will get it that with the Lyapunov direct method where we actually like bring the Lyapunov candidate function as, so of E1 transpose E1 plus E2 transpose E2. So now this is actually like positive all the cases because it is something like E1 squared E2 squared, right. So now when this would be 0, when both E1 equal to 0 and E2 equal to 0, then only the V equal to 0, right. So then you can see this is always positive definite that you can ensure. So now you differentiate this, so where E1 dot and E2 dot already we calculated and you substitute. So what you can actually like see that, so this condition is actually like fulfilling or not. You substitute that E1 dot you have already obtained and E2 dot also like you have obtained, okay, E1 dot you have obtained and E2 dot also like you can obtain in this way, and then what you can actually like see, so these two relations you substitute in this equation and that will give, you can say, the negative definite, okay. So in the sense what one can see, the closed loop stability also ensured. So now what you can recall this equation, so where you have substituted this, right. So this you recall, so what is E2? So E2 is actually like x2 desired minus x2. What is x2? In this case it is zeta, right. What is the x2 desired? So that is actually like x1 desired dot plus k1 E1, right. So what is this? So this is actually like what you can actually like feel it. So this is you can say this is not eta, this is eta desired dot. So this is k1, so eta desired minus eta, right. This is for the E2. What is x2 desired dot? So this is actually like you can differentiate this. So it is x1 dot and already you have actually like 1 dot which is actually like in the sense, so what you can see, this would be equal to eta double dot and this would be k1 eta desired dot minus eta dot, right. So in the sense you can see like these two are coming as it is what you have seen in the what you call the computed input control, where only thing here k1 and k2 are actually like playing a role. So that you have to actually see. So earlier we have taken simply kp and kd, but this would be combination of k1 k2 as a combination. So that is the major difference, but this would be ensure that this is completely asymptotically stable, whereas here you have to properly choose. But here what we have taken, the second order error dynamics of the overall system we have taken as, you can say, tends to 0, in the sense we have written as like this. So I will put it. So this equation we have actually like taken as 0. So where eta tilde double dot and eta tilde dot, so that actually like equation we have taken where k1 and k2 was actually like positive, there we have put kp and kd. These two are as long positive, this would be ensure. Right now here what we have modified as k1 and k2 are actually like positive, right. But what the difference between these two? So here everything we have written in the one single form called eta tilde or eta form in a very simple sense. So overall the position trajectory we have done in a inertial frame and we have understood everything in the inertial frame itself. Whereas in the cascaded you are actually like doing everything, the kinematic level in inner you call inertial space, and the inner loop you are doing in the body frame respect, in the sense you are doing with respect to actual body configuration. So, the dynamics you are trying to compensate in a body frame, where your kinematics you are correcting in the what you call inertial frame. So, that is why it is called double loop, or some people call it is actually like what you call cascaded or composite control. So, I will just to show it only one additional aspect. So, what that means? So, you can see like, so you are actually getting a robot. I will finish this diagram. So, what you are actually getting it? So, you are getting eta dot and eta. So, what we are actually like trying to do as a outer loop. So, in the outer loop, so I am actually like seeing that this is outer loop. In the outer loop, so you are actually like comparing eta desired and eta. So, that you are actually like making it along with what you are bringing the eta desired dot. So, once that is then what you are giving, so eta desired dot comma the eta desired and eta. So, this you are actually combining, and what you are giving the zeta desired you are actually giving. Once this zeta desired is given, then what you are trying to do, you are doing everything in the inner loop. So, that is why it is called actually like a dual loop or double loop, where the outer loop would be in a kinematic level and the inner loop in the dynamic level. So, that is what the beauty of this particular control. This is more common in the robotics community, whether it is a manipulator or mobile robot. This is one of the common phenomena used in, you can say, robotics. So, now this outer loop can be combined with other control strategy. Here we have done with a simple proportional control, whereas you can use something like LQR or learning based control or robust adaptive. Similarly, the inner loop even you can combine with, you can say something like a disturbance compensated control. All those things you can actually like incorporate. In the sense, you can see that these are two different segments. Only thing you have to actually like give proper desired vector for the inner loop. That is the only important thing, which is what you call the virtual control input that you need to give it to the inner loop. So, with that, so the control part is over. So, now we will actually like move to the, you can say, modern robotics, where we would see like what is the difference between what you call automated guided vehicle and autonomous mobile robot, and other aspect, what are the modern robot getting into a challenge, why it is actually like so difficult. So, all those things we will address in the next lectures. So, till then we are actually like saying bye, see you then.